Hello. So far in our exploration of compound interest, we've assumed that the banks will only compound our interest once per year, um, which is not really the case. Usually the banks will pay out their interest more frequently, but they'll pay it out in little pieces of interest. So we want to explore what happens when we compound more frequently. And we want to see what that does to one-time investments, as well as when we have a savings plan. So sit back and enjoy these videos. So we're going to start with exponential functions in their most basic form. So let me simply write that, pick a good color for this, f of x is equal to b to the x power. So if f of x equals b to the x power, hopefully you remember if we draw our axes, we're not going to worry about negative output values. Typically, if b is greater than 1, when you put a value in, when you put 0 in for x, anything to the 0 power is 1. When you put in values smaller than 1 for x, you have fractional powers of b. So let's say b was, if b equals 2, when x is something like 1/2, then f of x is really the square root of 2, which is smaller than 2. But if x is something like 2, then f of x would be 2 squared, which is 4, which is bigger than 2. And as x grows, f of x grows rapidly, and this is called exponential growth. If b is less than, so let me write next to that, that is if b is greater than 1, the function grows because you repeatedly multiply by a number greater than 1. Like in this example, we would keep multiplying by 2. If, on the other hand, b is less than 1, it flips the whole thing, and it's exponential decay. Because if b were something like 1/2, the more times you multiply by 1/2, the smaller something gets. You keep having it every time you multiply by a half. But if you go backwards in time, it was larger as you go in the backwards direction. So it's a flip of what b to the x would do when b is greater than 1. Now, obviously, with financial stuff, we're looking more at this case. So let's expand on that case. Now, we usually don't want to start with $1. So right now, if you put in f of 0, it would equal 1. And we don't want to have to start with $1 in the bank, or 1 euro, or 1 yuan, or whatever currency we're dealing with. We usually want to deal with bigger numbers than that. So we'll usually work with something more like f of x equals a times b to the x, right? And actually, I'm going to change this right now, since we're usually going to be working with functions of time. This is going to become f of t is equal to a times b to the t. Now, hopefully you remember what this a value does. It stretches the function vertically. So if I had an example of this, let me write f of t is equal to 200 times 1.05 to the t. When I put in f of 0, that becomes 200 times 1.05 to the 0. And hopefully you remember that anything to the 0 power is 1. So that's 200. So that would let me start with an investment that was, say, 200 rather than an investment that was 1. That number could easily be 2,000 or 200,000. So we're getting closer to what we need. Now, since we're talking about amounts of money, instead of calling it f of t, I might have a formula that looks more like a is equal to a0 times b to the t. Okay, or what we had been working with in the previous videos, I could use r, because we had talked about r sort of being the common ratio. But we could work with b and call it the base. Now, in either case, if we're doing financial stuff, we're talking about having some interest rate. So whether we're using B or R, B gets replaced by 1 plus interest rate. In the medical dosing, where we were actually taking something away, B ended up being 1 minus the, I'll call this amount removed. Let me call that, I'll just call that little a, and let that be the percent removed. So if 25% was removed, we ended up having 75% left, and B was 0.75. But that was when we were doing medical dosing. So now we're going to be dealing with bases that are bigger than 1. Recall that if the interest rate is 5%, that's 0.05 in decimal form, so the base would be 1.05. Okay, so continuing on, we can write that the amount of money that we have is equal to some starting amount of money times 1 plus I to the t power, okay? So far, we still are working with 1 compounding per year. Banks don't do it that way. Okay, it's much more common to compound. We'll start with a twice a year compounding. Okay, so I'm going to make a few changes here. Okay, and we'll do a hypothetical example, and then we'll do a general example. Okay, so let me make a little table. So let me put a background in here, and that'll help me with a little table. Let me put lines, a little graph here. Okay, so that'll make it easier to draw my table. Okay, so let me do this in blue. Okay, so here we go. Let's have the n equal the compounding number. Compounding, I should say frequency. Okay. And then we'll have a example. If let's say if the interest rate is 6% annually. Actually, let me change that to 4%. It'll work out more nicely. Let's work with 4% annually. Okay, then let's move to a specific formula. Okay, let's assume for the specific formula that we're doing a $100 investment. And then we'll generalize. So then we'll have a general formula. Okay, so let's start with n equals 2. This is called semi-annual compounding, meaning twice per year. All right. So what happens to our interest rate? Okay, if we're going to give interest twice per year, we are not going to give 4% twice a year. What we're going to do is give 0.04 in decimal form divided by 2. So we'll give 0.02, but what will happen, we'll give it twice per year. Okay, so draw a line in here. Now, how do we change the formula if we're going to give twice per year? Okay, so we would have that the amount of money we have, we said we're going to start with $100. Okay, so instead of giving 4%, we'll do 1 plus, I'm going to write it as, we'll write it as 0.02. But we're not going to give it once per year. We're going to have compounded. By the time t equals 1 year, we're going to have compounded twice. So what do we need to do? We have to put 2t right there. okay? Um, so we'll work with that. And we can see in general, this would have been A is equal to A naught times 1 plus I over 2 times 2t. So we're going to cut the interest rate in half, but we're going to give it twice as often. It turns out you'll get a little bit more interest that way rather than doing it once per year. Okay, so the next example would be if n equals 4. So this is what happens if you give your interest out quarterly. This is more common than giving semi-annual interest. But if we're going to do that quarterly, then we would take the 0.04 of interest and we would divide it by 4. So that would mean each time we would give 0.01, but we would do that 4 times per year. All right, and so A would equal 100 is our starting investment, and we would do 1 plus 0.01, and we would end up doing that 4 times per year. So by the time t equals 1, we had to compound 4 times. By the time t equals 2, we will compound 8 times, and so on. So we're using, let me just point out here, we're giving less interest, but we're doing it more frequently, and that turns out to give a little bit more interest over time. So let's go back to getting a general formula. So this would be A equals A naught times 1 plus I over 4 times 4t. All right, let's keep going. The most common thing in banking is to do it 12 times per year, which would be monthly. As we start talking about things like paying mortgages, those are going to always be factored in 12 times a year. So you're going to pay every month. Paychecks often come in monthly. So investment plans are often done in a monthly fashion. So a month is a really important time period when you're working with finance. So what would we have? We would have 0.04 divided by 12. Okay, so suddenly this doesn't come out quite as cleanly, but this will be 0.0033. Be repeating, but we'll stop there. But this will be given 12 times per year. Okay, so what happens? A will equal the $100 we have. We'll add the 0.0033 of interest, but we'll do that 12 times per year. So that would become 12t, all right? And we could keep on going, and this will be A equals A naught times 1 plus I over 12 times 12t. So once again, we're giving a 1/12 of the interest that it states as the annual rate, but we're doing it 12 times per year. And this will in fact turn out to be a little bit bigger than what we would have gotten if we just got the annual rate. Okay, let's just do one more. So instead of doing it monthly, we could obviously go to weekly, we could go to daily. Let's just do daily. So that would be, let's just assume it's a year with 365 days. So we would compute the interest rate daily. So we would have 0.04 over 365, but we would do it every day. And I'm just going to jump right to the last column, and that would be that A is equal to A naught times 1 plus I over 365, but we would do that 365 times per year. So we can come up with a general formula. So we can say in general, if n equals the compounding frequency, we can say that A is equal to however much we put in times 1 plus I over n. So we'll give 1/n of it. However many parts n is in the year, we'll divide I by that many parts, but we'll give it out n times per year. So we will multiply the time by n in order to figure out how much this is. Now, one thing that you may have learned in chapter 4 last year was if I take the limit as n approaches infinity of 1 plus 1 over n to the nth power. We get this thing called e. Okay, we get this irrational number called e. If you want to see what the number is, look at the e button in your calculator. It's right above the logarithm button. So if you say second function logarithm button, you'll get e to the x. Type in a 1 for the x value, and you'll get what the value of e is. It's roughly 2.718. But it's irrational like pi, so it goes on forever. Now, if we change this to be the limit as n approaches infinity of 1 plus the interest rate over n to the n power, this ends up being e to the I. So if we were to throw in a factor of t here, if I were to put a t here, this would be e to the t. If I put a factor of t as part of the exponent, this would be e to the it. Often we'll say that is e to the rt because I can get confused with the imaginary number, the square root of -1. So it often is written as e to the rt. But in our text, when we talk about the interest rate, they use the variable I. So that will be helpful. Now, it can be shown relatively easily that if you compound more and more frequently, you do in fact approach the same answer that you would get if you did e to the it. So let's just look at real carefully with the example we had. If I took 1 plus 0.04, let's do it twice per year to the 2. And then we'll do it 1 plus 0.04 over 4. So we'll do it quarterly to the 4. All right. And then let's look at it monthly, 1 plus 0.04 over 12 to the 12. I want to compare that to e to the 0.04. All right. So I'm going to pause and calculate these out, and we'll see what happens with these. Okay, so I've computed the numbers. Now I want you to notice a trend, a couple trends, okay? First of all, as I compound more frequently, this gets slightly larger. Now you may wonder why the bank would want to pay me more money. They want to make as much money as possible. But where they make their money is by lending the money at slightly higher interest rates than what they're paying to me. So I give them money and they turn around and lend it out to small businesses or to homeowners who want to purchase a house. And they will charge the homeowner or small business just a little bit more money. So the more frequently they compound it, the more they're actually charging. It means they have to pay me a little bit more, but since my interest rate is lower than what they're lending it out for, they would rather compound more frequently. So they probably do it monthly as they're doing it. They don't want to do it daily because then they have to recalculate all the numbers in the bank every day, and that's a little bit more time consuming. So they do it on a monthly basis for the most part. Now, you can also note, this is the other important thing, that as we compound it more frequently, we get closer and closer to this number. So this is sort of the asymptotic value. So we could make this 12 into a 365 if we wanted to do it daily. And we would see that we would get extremely close to what e to the 0.04 is. Now remember, the 0.04 here corresponds to the interest rate. So this e to the 0.04 represents what would happen if instead of doing it every day, we did it every nanosecond, okay? Or actually more frequently than that, because a nanosecond is a discrete amount of time. So if we were to continuously compound it, our interest for the year would end up approaching, would be this number. So as we compound more and more frequently, then we get ever closer to that number. And at some point, you might as well just treat it as continuous compounding because the formula is much easier if we can say that, let me switch colors here, A is equal to A naught E to the RT. That's a much simpler formula to work with than the complicated formula that we have right here. But for the most part, we'll probably stop at n equals 12. So it's better to use the more complicated formula. All right, I'll continue with some examples in the next video.